Okay, welcome back. Today we're going to cover class number 8. We had a snow day last class, so I've updated the calendar. I shoved everything down a class day. I've got a new calendar on the table, so grab one of the updated calendars. Due today, project number 2. It was supposed to be due Monday, but throw project number 2 right into the folders. Also due today, quiz number 2. That was the memorized derivatives and antiderivatives quizzes. Technically, that was due Friday, but we kind of had another snow day Wednesday last week, so we made that one due Monday. But then we had a snow day, and so now it's due at this moment. So throw quiz number 2 in whatever completed form it is in inside of the folders. Also today, project number 3 is assigned. Go ahead and grab one from the table. So lots of stuff shuffled around by snow days, but I think we're on track here. Okay, so today we're going to cover something called integration by parts. Next class, that's an integration technique. Next class is another integration technique, and then we will kind of summarize our integration techniques the third class from now. Questions on the new calendar? So again, everything's been shoved down a day. So if you're the kind of person that wrote in your calendar or typed in your calendar, like the dates of tests, those are all wrong. So make the changes according to this new piece of paper. Okay, so here we are on page 73 with our daily summary. In this class, we learn a brand new technique called integration by parts. It's basically the antiderivative version of the product rule for derivatives. Number 1, are we able to calculate the simple looking integral of 3x cosine of x dx? So it's not one of our basic integrals. It's not in our very, very small list. Can I separate like two different integrals? Like one of them is 3x and one of them is cosine x? Can I separate the integrals that way? No, there's no product rule separating integrals there. Can I pull the 3x outside? Because that would make life easier. There's an x, can't pull any variables outside of the integral. And then the only other technique we have is u substitution, but try as you might, there isn't any u substitution that's going to work on this integral. So a brand new technique, it's called integration by parts. It's got this formula, integral of u dv is equal to uv minus the integral of v du. We're going to see that formula in action right now. It's just letters floating around. Both u and dv are going to be functions of x, as we will see. You can check out the derivation of this formula in the book, but we're just going to use it here today. So let's give this one a shot. All right, so first thing we are going to do is try to make it so that the integral that we start with matches exactly the left-hand side of this crazy looking formula. So I want to pick u and dv to be the sum of the factors that are inside of there. I'm going to make this choice here, and then we'll talk about, like different options for u and dv. Okay, so the u that I'm going to pick is 3x, and the dv that I'm going to pick is cosine of x. And we always want to make sure that the dx goes into one of these pieces. It's always going to go into the d piece, the derivative piece. So just like that. Would you guys agree that the two yellow things are exactly equal given the choices that I've made? We could have made other choices. Like I could have swapped, could have put cosine of x on one and 3x on the other. Turns out that's a bad choice, but it's not illegal. Okay, and then we're going to look at the right-hand side. So the right-hand side involves this expression right here, du, which is really shorthand for du dx. It's the derivative of u with respect to x. So you find the one equation that says u equals, and you take its derivative, okay? And so I'm going to come over here and I'm going to say, okay, I'm going to write this in a slightly different way. So hopefully you have a pencil for this piece. What is the derivative of u with respect to x? 3, right? Derivative of 3x is just 3. But we're always going to take that dx and multiply it to the other side. So I'm actually going to erase it right now. And I typically don't even write the step that I wrote there on the left-hand side. I just immediately jump here, okay? So the derivative here is 3 dx. Okay, we also need to calculate v. At the moment, we have dv. And if you feel like it, you could imagine this dx is being under here. I'm going to get rid of that in a second. But this is telling me that the derivative of v with respect to x is cosine of x, what should I do with that thing to get from the derivative of v to v itself? Take the antiderivative, right? So we take an antiderivative over here. I'm going to put that dx back on the right-hand side. We like it there. And we take an antiderivative here. Antiderivative of cosine, is it sine or is it negative sine? An antiderivative of cosine is positive sine. Be really careful with pluses and minuses there for sine and cosine. What's a good name for this thing? That is v. We just found the antiderivative of dv dx. It is called v. Okay, and so when I do integration by parts, I always set it up this way with my u and dv across the top, and then I take a derivative on the left and an antiderivative on the right. Always works that way. And now that we've got all of our pieces, we're ready to use the formula that's given up there. And so the formula says that the original integral highlighted in yellow is equal to u times v minus the integral of v times du. And if you write these pieces in exactly these spots, then for me, it's just a pattern that I follow with arrows. U times v is always this diagonal, minus the integral of v du. That's always going from right to left in the bottom row. So that's the pattern that I remember with a minus and an integral sign. So this yellow formula, according to that pattern, u times v, 3x times sine of x, minus the integral across the bottom row, sine of x times 3 dx. No, typically there'll be x's floating around there on all four pieces. Yeah, it's a good question. So we're going to see more complicated ones in today. Yeah. Okay, so does everybody buy that we've applied this formula to get this thing in black here? Sort of follow the bouncing ball. Now, integration by parts is not a cure-all, it's a swap. We started with an integral. What do we have now? An integral, right? So you still have to do an integral. The hope is that the integral we end up with is better than the one that we started with. So in this case, it is, because what can we do with this 3? Pull it outside, and then we get the integral of sine of x, which is one of the few things that's in our list of integrals. So let's write our answer here. 3x sine x minus, I'm pulling the 3 outside. What's the integral of sine of x dx? Is that cosine or is that negative sine? Sorry, is it cosine or negative cosine? It is negative cosine. And then at the end of every indefinite integral, what do we put? Plus c. That's it. And then we'll just clean this up a tiny bit. 3x sine of x minus times minus makes plus 3 cosine of x plus c. Okay. That integration by parts formula that I showed you, you have no reason to believe it's true. But again, we can check every single antiderivative once we found it. What do we do with that thing? Take the derivative. What are we hoping to get? What color? Color is not typically a math question, but what? Blue is not the right answer. We're trying to get yellow. Yes? We want to get that thing that's up there in yellow. All right, let's take a derivative. We'll do it over here. Check. Okay, derivative of 3x sine of x. What derivative rule do we need to use? That's the product rule. So we do first times derivative of the second. First times derivative of the second, cosine x. Plus second sine x times derivative of the first, 3, right? 3x is our first, times 3. Okay, that's that part. Plus, now we're doing the derivative of 3 cosine of x. What's the derivative of 3? Is negative 3 sine of x. Derivative of that plus constant is nothing. And then what nice thing happens? Negative 3 sign, positive 3 sign, and we're left with yellow. Okay? So this is how we undo the product rule. It's integration by parts. Okay, another observation here. I chose to put the 3x in the u slot and the cosine of x in the dv slot. We could have made the opposite selection. Suppose that for 1 second here that we put 3x right here. 3x dx. Remember, when we go down on this side, we're taking an antiderivative to get from dv to v. What's the antiderivative of 3x? 3x squared over 2. Okay, fine. And then when we follow the arrows, we multiply here and then we multiply there. And when we go on the bottom row, that's where we get our integral. And the integral that we get is going to have a 3x squared in it, along with a sine of some flavor, sine of x. Is 3x squared sine of x better or worse than the original? 3x squared sine of x. That's worse because it's got an x squared in it. Whereas the choice that we made, what happened to that x when we took the derivative? It got better, disappeared, right? And so you got to be careful about the choice that you make. So roughly speaking, you want to put something in the du that's going to get better when you take a derivative, and something in the dv that's not going to get too much worse, right? Cosine to sine, that's no worse, right? It's like an even swap. But 3x to 3, that's definitely better. Okay, let's do some more practice. Part B, integral from 1 to e of ln of x dx. There's a hint there that we'll take advantage of soon, but let's start with our same pattern, u and dv. Okay, this one is a little bit unusual. Typically, u is one of the factors and dv is the other factor, but how many factors are inside of this integral? Just the one, it's just ln of x. Don't copy this. If I put ln of x over here, what do I need to do to get down below? I need an antiderivative, which I don't know how to do. So let's not do that. So we got no choice but to put the entire integrand over there on the left. I do have to put something on the dv part. What am I putting? Yeah, it's a 1 and then a, remember we'll always put the dx over there on the dv side. Okay, going down here, we're taking a derivative. It's the derivative of ln of x, 1 over x, and then don't forget we're putting dx every time. What calculus thing are we doing here on the right? Antiderivative, right? Derivative there, antiderivative here. Antiderivative of 1 dx, x. That's it, right? Turns out you don't need to put a plus c there. I mean, you can, but it's going to disappear at the end of the day, so we'll just choose c as 0 every time we do this. We will put a plus c at the very end of the day, but no need to do that at this early stage. Okay, we've kind of broken our cardinal rule. I said put something in the dv that doesn't get much worse. I would say that x is definitely worse than 1. It's more complex, but something good is going to happen. If you sort of take a sneak peek at the arrows here, what's going to happen when we multiply on the bottom row? The x and the 1 over x are going to cancel, and we'll get an integral we can do. Great. So this integral, I'll just call it I up here, is equal to, so we follow the arrows. So it's that diagonal, ln of x times x. What's the next operation? Minus. What's the next symbol? Integral. Always minus the integral on that bottom row. X times 1 over x dx. Okay, this was a definite integral before. It is still a definite integral with exactly the same limits, 1 to e. But here's the deal. This original integral, at the end of the day, is supposed to be a number, right? Just going to be one single number. But this thing over here, at the moment, is variables. And that's not okay. It's supposed to be a number. And so we need to plug in the 1 and the e into this guy right here. And so that's what this formula is telling us. It's saying when you do UV, that was this diagonal, you plug in and you subtract just like you normally do in the normal order, top minus bottom. And then here, you still put the same limits. So let's go ahead and put in this guy evaluated between 1 and E. So this equals, okay, so let's plug in. When I plug in E, I get ln of E times E minus, and then we plug in 1, ln of 1 times 1. So that's the first part, minus the integral from 1 to E. And we said x and 1 over x cancel. So we just get a 1 dx right there. Okay, so now we're doing some calculations. ln of E is a nice number. It is 1. So this first guy is just E minus ln of 1 is also a nice number. It's a 0. So I get that. And then the integral of 1 dx is x. And then we evaluate that guy between the same 1 and E. So E minus, and then we plug in E minus 1. Questions on that one? Okay, so we just figured out how to integrate ln of x, which is a brand new antiderivative for us. We have now found something whose derivative is ln of x. I guess technically I didn't write it all in one shot here, but we can. Integral of ln of x dx is equal to, so we had the first part. I'm going to write the x in the beginning. X ln of x minus, and then the second integral became an x. So there's your antiderivative of ln of x. Okay, so when we're ready, we'll move on to the next page. Okay, integral of e to the 2x times sine of x. We'll just run through our very small list of things we know how to anti-differentiate. That's not one of them. There's no u substitution that's going to help us here. You could let u equal 2x, that's fine, but the sine of x is really completely unrelated to the e to the 2x. So these are two functions multiplied that have nothing to do with each other, and that's sort of one of the calling cards for integration by parts. Okay, let's give this one a shot. This is going to be tough. I hope this problem is the worst thing that happens to you today. Here we go. U equals dv equals. Okay, turns out it makes no difference which one goes where. You've got e to the 2x and you've got sine of x. I'm going to put e to the 2x here and sine of x dx over there. If you're a glutton for punishment, try this problem again later and swap those. You'll get the same answer at the end. Okay, in the first column, we're taking a derivative. Du equals, yeah, so 2e to the 2x, don't forget the dx right there. And e to the stuff times the derivative of the stuff. V equals, so again, be really careful. Is it cosine or is it negative cosine? I'm hearing both answers right now, so we cannot move on. Right, and so this is one thing that makes these hard, is that derivatives and antiderivatives of sines and cosines, they just go back and forth, but with negative signs, depending on which way you're going and which function you start with, and then you have to know them really, really well. Okay, so antiderivative is negative cosine. All right, so let's follow our arrows here, this way and then this way. Again, I'll give this guy a name, call it I equals. Okay, so following the arrows, multiply the first diagonal, e to the 2x times negative cosine of x minus the integral, multiply on the bottom, negative cosine x times 2e to the 2x dx. Okay, let's clean this up just a little bit. I'm going to pull that negative in the front. So we got negative e to the 2x cosine of x. And then I see a minus, and inside that negative sign, I'm going to bring outside to make a plus. What else can I bring out of the integral? It's the 2. We've got 2 integral, and I'll just shuffle it around e to the 2x cosine of x dx. So check me there, make sure everything is still there. Okay. Yeah, it became positive when we pulled the negative outside. Okay. All right. Again, the hope with integration by parts is that the integral you come up with is better than the one that you started with. So would you say that this one is better, worse, or about the same as the one that we started with? It's about the same. We've still got e to the 2x. Instead of sine, we've got cosine, but that's basically the same. So it doesn't appear that we've made any progress. Okay, turns out we just have to persevere. If I just gave you this integral right here, forget where it came from. What technique might we try? So I don't think a u will work for the same reasons that it didn't work on the original, is that e to the 2x and cosine of x really have nothing to do with each other. So maybe integration by parts would be something to try. I know it doesn't seem promising at this moment, but let's give it a shot. So I'm going to highlight this integral right here in green and say forget about everything else. We're just going to focus on trying to do that integral, and we're going to use integration by parts. Okay, so u equals dv equals. Okay, your choices are e to the 2x and cosine of x. Remember how I said when we started this, it didn't matter which choice we made at the beginning? I said you could have swapped the u and the dv from what I chose. Okay, now we have to make the right choice. We have to make the same choice that we made up above. What was the choice I made for u for the first time around? E to the 2x. We better make the same choice here. E to the 2x right there, which means what is dv? Cosine x. This specific one here. Okay, and then we'll take our derivative here. What is it? 2e to the 2x. Don't forget the dx. Take an antiderivative here. All right, no fooling around. Is it sine or is it negative sine? Sine or negative sine? One table says sine. Another table says sine. The other two tables, yeah? Sine. Good. Okay, let's follow our arrows. Diagonal, and then across here. So I am just doing that thing that's highlighted up there. Is that what I want to do? No, I'm going to do the whole thing actually. So I equals. So I'm going to copy everything, and then we're going to use our integration by parts formula on the highlighted stuff. So we've got this negative e to the 2x cosine of x, negative e to the 2x cosine of x, plus 2, and then I'm going to put big old brackets, and then I'm going to highlight this one ahead of time. All of this is going to be equal to the green highlighted stuff using our integration by parts formula. So that's in red here, so we're just following the arrows. So multiply on the diagonal. E to the 2x times sine of x minus the integral. And we multiply across the bottom. Sine of x 2e to the 2x dx. Make sure you see where all of those pieces came from. Do we buy the two highlighted green things are equal? Okay, let's distribute just a little bit here. Equals, copying this first guy, negative e to the 2x cosine of x, plus, okay, now I'm going to distribute the 2. So we go 2e to the 2x sine of x. And let's go ahead and take that 2 in the integral outside of the integral, but it's still going to get multiplied by this 2, which distributes in. So minus 4, integral e to the 2x sine of x dx. Make sure you're comfortable with that step 2. All right, so we distribute the 2 in the front of the brackets, and we pull out the 2 that's in the integral. Okay. All right, so again, integration by parts trades one integral for another integral. Take a look at this integral that we have here and compare it to the original one from way back at the top. Better, worse, or about the same? It's not even about the same, it's exactly the same, right? This integral is exactly the same. So it feels like we've just spun our wheels and we've taken an integral we couldn't do and we traded it for another integral we can't do plus a bunch of gobbledygook. But there's a little twist here that's going to allow us to finish this problem in no time flat. The calculus is actually done already. We're not doing any more derivatives or antiderivatives. I had been calling this I, but I'm just going to recopy the original integral here. So this is equal to the integral of e to the 2x. What? Sine of x. I said this is going to be the worst thing that happens to you today. Oh, dx equals. Okay, everybody buy that? This was the original integral we started with. It's equal to all of this. All right. Suppose that we just temporarily in our minds substitute the letter y for the entire integral over there, which means that this thing here is also a y. And in fact, there's like a minus 4y there, right? And then there's a bunch of stuff in here. If I asked you to solve this equation for y, what would you do? You'd add the 4y to both sides, giving you 5y, and then you divide by 5. That's what we're going to do. So let's add the 4 of those over here. So that gives me 5y, 5 of those integrals, e to the 2x sine of x dx equals all of this gobbledygook, negative e to the 2x cosine of x plus 2e to the 2x sine of x. And then trying to solve for that integral, we divide by 5. I'm not going to rewrite it. Every indefinite integral has what at the end of the answer? Let's see. This one I really do need to pull out of a hat because we never actually did an integral, right? We just kind of like backdoor solved for the integral that we wanted because it came up in 2 different places in our equation. And that's it. That's it. It's as simple as that. Okay. Number 4, just kind of some conclusions here. Integration by parts is kind of a way to undo the product rule, and it transforms an integral involving the product of 2 functions into another integral, which may or may not be easier to deal with. Expect that you're going to make some bad choices for u and dv as you gain experience here, and that sometimes you're going to pick poorly, and you're going to end up with integrals that are worse than the ones that you started with, and then you'll try something else. Furthermore, integration by parts is good for integrating products of 2 functions, one of which gets better when you take a derivative, and the other of which doesn't get much worse when you take an antiderivative. Parts is also a good technique for to consider when integrating an inverse trig function. We have not seen any of those, but if you wanted to integrate inverse sine, it turns out integration by parts is the way to go, or a log function. We integrated ln of x today by using integration by parts. Couple of suggestions for you, but these are just general. This is not like it will always work, but letting u equal ln or inverse sine or inverse tan or polynomial typically means that the you will get a little better when you take a derivative. And then some suggestions for dv. Remember, typically you put things here that don't get much worse when you take an antiderivative. Sine, cosine, e to the x. When you take an antiderivative of sine, you get cosine, maybe with a negative. When you take antiderivative of cosine, you get sine, maybe with a negative. What's the antiderivative of e to the x? E to the x. So good things to put over there because they don't get worse when you take antiderivative. Okay, activity starts on the next page. Let's see how far we can get.